Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial and System Engineering. This lecture is on other time series methods. And in this lesson and the one following, I will conclude this lecture and this course with a general modeling framework that for multivariate time series called functional data analysis. The models discussed so far are all linear models in the sense that they capture linear dependencies with respect to the past history of the time series. A framework which allows estimation of non-parametric relationships and dynamics between time-varying processes is the so-called functional data analysis. Functional data are defined as multiple processes or so-called random functions which depend in our context on time, although they can depend on other functionality designs, for example, space. We have n such random functions or time series, each one observed at a set of time points denoted here Tij for the ith random function or process. The time points do not need to be the same across all the random functions. We can also have a fixed design when the time points are fixed in advance, but also random when we have observations of the random functions at random time points not known in advance. Last, unlike time series analysis, the time points can be observed sparsely or densely, depending on the experiment generating the random functions. The field for analyzing such data is called functional data analysis. These are examples of such functional data. The two examples on the left are for sparse design of time points, whereas those on the right are for densely observed time space or dense design of time points. The difference between the examples of functional data displayed on the top versus on the bottom plots is that those on the top have a random design, whereas those on the bottom have a fixed, equally spaced design. Within each of the four plots, each line crosses the functional observations sampled from two different random processes at varying time point. The two processes differ in the mean and the covariances matrices. The observations can be made sparsely or densely over the time period, and they can be made at time points with a fixed, equally spaced in this case design, or at random time points over this time period, as illustrated in those four examples. We can add random errors or disturbances to these functions and thus obtain the functional data as provided on this slide. Similar characteristics in terms of the design points are for this functional data. However, because of the random disturbances, we see that the patterns of the functions are less clearly distinguished, particularly for the sparse design. The idea of functional data analysis is to borrow information across multiple such random functions to make inferences on the process generating the functional data. This is particularly the case when the design of time points is sparse and or the functions are observed with high measurement error. Thus, the difference between classic time series analysis and functional data analysis is that in classic time series analysis, we draw inferences on a time series given past history alone, whereas in functional data, we make inferences with the aid of repeated realizations of the same or similar processes. General characteristics of function data are as follows. Function data are measurements or realizations of smooth processes over time plus noise, thus with no drastic change points or discontinuities. They are commonly non-stationary processes with time-varying first moment or second moment. And in fact, the focus is on estimation of the first and or second moments of the generating functional process. We usually do not want to make parametric assumptions about those processes. We use non-parametric or semi-parametric approaches to estimate the first and second moments of the generating process. Often we have multiple measurements of the same process or repeated measurements of multiple processes, also called multi-level functional data. In the analysis of functional data, we study the distribution of the process generating the functional data along with the relationships between function random variables and relationships between function random variables and other quantities. Functional data analysis methodology has focused on many areas of research. For example, two of the most common objectives are representing the data in ways that aid further analysis through functional clustering, or studying important sources of pattern and variations among the data through functional principal component analysis. Functional data can often be observed shifted in time, and thus alignment or registration of the functional data can be used to display the data to highlight various characteristics of the generating process. Methods for explaining variations in an outcome or dependent variable by using independent variable information, such as functional regression analysis, is one of the largest areas of methodological development and application, since it can capture relationships and associations between complex processes. For example, one may extend the linear regression model to the so-called time-varying regression model, in which the regression coefficients are not constant, but are functions varying in time. Such models can capture relationships between a response variable and multiple time-varying predicting variables. Functional data analysis is now a very active field. You will find many methodologies already implemented in the R Statistica software. In the last lesson of this lecture, I will briefly illustrate functional data analysis with one specific methodology. In summary, in this lesson, I introduced yet another statistical modeling framework, so-called the functional data analysis. Thank you. Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial and System Engineering. This lecture is on other time series methods. And I will conclude this lecture and this course with one particular method in functional data analysis called functional clustering. In the analysis of functional data, we study the distribution of the process generating the functional data, along with relationships between functional random variables and relationships between functional random variables and other random quantities. Functional data analysis methodology has focused on many areas of research. One of the most common objectives is representing the data in ways that aid further analysis through functional clustering, which I will briefly introduce in this lesson. Functional data clustering has many applications. Among applications that I explore in my own research using functional clustering are clustering subjects by some health outcomes related to a condition. For example, the treatment care pathway for pediatric asthma for over 500,000 children in the U.S. Another example is summarizing the market value trends for many manufacturing companies to better understand the overall trends in the manufacturing industry. A third example is summarizing access to financial services estimated at the community level for communities in the states of Georgia, for capturing potential disparities in access as it progressed over more than 10 years. And fourth example is profiling gene expression from microarray studies to identify genes which respond to a treatment for diabetes. In clustering analysis, there are two types of research methods: hard clustering, which partitions the set of random functions into non-overlapping subset of random functions according to a similarity measure, and soft clustering, in which the clustering membership follows a multinomial distribution. In other words, each function is assigned to one cluster with a probability value. For example, if there are 3 clusters, the function may be classified with probability 0.1 as being the first cluster, with probability 0.6 in cluster 2, and with probability 0.3 in cluster 3. Thus, there is not a hard partition of the set of random functions into clusters. Hard clustering is commonly applied to identify or estimate predominant functional trends in the functional data. The underlying patterns identified with hard clustering can be viewed as a dimensionality reduction method from potentially a large number of random functions to only a few patterns characterizing the entire set of observed functions. What does hard clustering mean? It means identifying a clustering map from the set of pairs of any two functions in a set of functions to be clustered, which is called here on the slide F. And the clustering map takes values 0 or 1 only, where the clustering map is 1 if the pairs are in the same cluster, and 0 otherwise. Thus, the clustering map T induces a partition of the set F, the functions F, with k different partitions or clusters. In what follows, I will present a method that I published in 2005 on how to derive such a clustering map. Our first step is to transform the set of random functions into a transform domain and cluster the transformation coefficients rather than the random functions. This transformation is similar to the idea of spectral analysis discussed in one of the first lessons in this lecture. For the transformation, we can write the expectation of the random functions using non-parametric regression, non-parametric decomposition, given a basis of functions, for example, the Fourier basis discussed in the introduction of the spectral analysis. Then estimate the parameters in this decomposition, thetas, to obtain an estimation of the expectation of the random function ft. We can apply this procedure to all random functions to be clustered. A second step is to identify an appropriate similarity measure. A common similarity measure for functions is the correlation function, which measures how similarly the shapes of the functions are. But we cannot apply this dissimilarity measure directly to the random functions since they are functions observed with measurement error. Moreover, many clustering algorithms apply under the Euclidean distance between two objects, for example, the k-means clustering algorithm. To address these challenges, alternatively, we can cluster the transformation coefficients theta hat instead of the random functions. In fact, if we use the appropriate basis of functions, for example, the Fourier basis of functions to decompose the functions, then it can be shown that clustering using a similarity measure, the correlation between two functions, is equivalent to clustering using a similarity measure, the Euclidean distance between their transformation coefficients thetas. Thus, after we apply the first step, the transformation from the functional domain to the transform domain, as I provided in a previous slide, we can apply the classic hard clustering algorithm, k-means, for example, to obtain the partition or the clustering map T. Note that it is not correct to apply k-means directly to the observed functional data due to the functionality or dependence between the observations of each random function. Here's an example where the application is to cluster temporal gene expression profiles, where each profile corresponds to one gene, reflecting how the gene responds to a specific treatment for diabetes. Note that not all genes considered will respond to the treatment, and thus it is expected that many gene expression profiles to be constant. It's also expected that some genes will show some up expression pattern where other genes will respond to as a down expression pattern. On this slide, I plotted all the gene expression profiles considered in this particular experiment. The time is between 0, or the baseline, no treatment, to 1,450 minutes. From this plot, we do see that we have a large number of non-informative profiles. That means they are non-constant. We also see that there is a low contrast to noise ratio within each profile in the sense that the error term is large as compared to the signal provided by the expected function or profile. These are common features in functional data. Clustering can be impacted in terms of accuracy of the clustering by the presence of a large number of non-informative or constant profiles, as in this example. Thus, a first step is to identify those profiles which are non-informative. For this, I performed a hypothesis testing procedure in which the hypothesis is that the profile is constant versus the alternative that is not. These two plots show the partition of the profiles into those for which we do not reject the null hypothesis in the left plot, and of those for which we reject the null hypothesis and this informative in the plot on the right. The last step is to apply the clustering algorithm to the profile as identified as informative or non-constant in the previous step, in the previous slide. Using the approach I described in this lesson, in which we first transform the random functions, then apply k-means to the estimated transform coefficients theta, we obtain this very simple clustering of the expression profiles. As we partition the set of the profiles into these two clusters, we can now clearly see two distinct patterns. This was not apparent from the plot in which I plotted all the random profiles, all random functions together. This last slide provides a general framework for soft functional clustering. Here we assume that clustering is a random variable defined here as z, which is not observed or it is hidden. A similar concept of hidden variable came up in the description of the state space models. The only observable data are the random functions with I from 1 to n. In this framework, the clustering is assumed to follow a multinomial distribution, saying that zi takes label c with probability pi c, where the labels are the clusters. Ideally, we would have the complete distribution, both the yi and zi, but we do not observe z, and thus we'll need to impute the cluster membership z while also estimating the mean cluster patterns of each cluster. To do so, we return to the maximum likelihood approach, but this time we use the so-called expectation maximization algorithm, which iterates over two steps. At the expectation step, we impute the cluster membership or the hidden variable z. At the maximization step, we maximize the likelihood of the conditional distribution of y given the z imputed from the expectation step. We iterate these two steps until convergence. The final output is the imputed cluster membership z and the estimated cluster patterns. As you may gather, this approach is much more involved in terms of modeling and estimation, and thus I'll leave it at that. In summary, this last lesson introduces advanced statistical modeling for clustering functional data. Thank you.